Unit 3, intermolecular forces and properties, and how individual molecules interact with each other to form solids, liquids, and gases. Okay, so a great example is water. We see water in all three forms all the time. We use these numbers in chemistry 1, the enthalpy of fusion and the enthalpy of vaporization. Fusion means that you're going from a solid and you're turning it into a liquid, so it's melting. And vaporization means it's turning into a gas. Yep, it's vaporizing. So from a liquid, yes. So if you notice just the energies associated with them, the molar heat of fusion is a lot smaller than the molar heat of vaporization. So what that means is it takes a lot less energy to change from a solid to a liquid for water than it does to go from liquid water to gaseous water. So that's why when you just get an ice cube out of the freezer and it melts, because eventually it's just gaining energy enough to do that, it doesn't take so much. But in order to get water to turn into a vapor, you might have to boil it, or you have to add a lot of energy to it in order to break that down. Another unique property of water is that solid water has a lower density than liquid water. So that's what's in this table 10.1 over here. And that's the reason why ice cubes melt, or ice cubes float in your drink. Does anybody have a guess as to why the density is less? Yeah, and when it freezes together, the structure gets bigger and there's holes in the structure, and so it creates air pockets, which helps make it less dense. So water is very unique in that regard. Remember last year in Chem 1, or 2 years ago, we did a project like the Universal Solvent Project, where we threw water at people. Yeah. But so water is just a really, sometimes it follows the trends and sometimes it doesn't, but it is a good example of these. Okay, so.
Are you going to use that as an example this year? No.
Probably not. I don't know, I haven't, so we'll see. We'll see. We'll see.
No, you should be like, this is what not to do.
Okay. Okay. So we talked about in the last 2 units that the bonding in between atoms is called intramolecular bonding. So you have to be very careful. Intra means within. Okay? So the types of intramolecular bonding, what do we have? If you had 2 elements, what could a type of bond be between them? Ionic. Yeah, what else? Think about the lab. Covalent. Could be polar or nonpolar, covalent. What else from the lab? Metallic. Yeah. So all of those types of bonds are known as intramolecular bonds. Okay? In this chapter, or in this unit, I should say unit, we are not going to focus so much on what's happening within the atoms. Instead, we're going to focus on the forces that hold different molecules together. And so those are called intermolecular forces. So there's a difference there. Inter means outside the molecule. Intra means within the molecule. Okay? Remember that when a substance changes from a solid to a liquid to a gas, the actual molecule itself remains intact. Like water, this is a picture or a thing of water, the actual H2O molecule doesn't change. What changes is how the waters are interacting with each other. Okay, so the forces among the molecules, not the actual molecules, are what change in order to change your state of matter, or it's also called a phase change. The first type of intermolecular force we're going to talk about is called a dipole-dipole force. So as we saw in Unit 2, molecules with polar bonds often behave as if they have a center of positive charge and a center of negative charge, meaning they have the dipole moment. And remember, we drew arrows with dipole moments, right? Where the arrow pointed towards the negative side, and then it kind of had like a plus side by the positive side. So the dipole means it's pulling to the negative side. Which side is more negative? When molecules with dipole moments attract to each other and align so that the positive and negative ends are close to each other, We call this a dipole-dipole interaction. So in this picture, the attractions are the red lines, and if you notice, like, the positive side is connecting to the negative side of two different molecules, and again, negative to positive there. So these interactions that we're talking about are as if we have a bunch of molecules interacting with each other. It's different than just one molecule, which is what we've been talking about so far. So you have to know that distinction. And dipole interactions happen when you have polar molecules, okay? So dipole-dipole forces are typically only about 1% as strong as covalent and ionic bonds, meaning that they're a lot weaker. Intermolecular forces are a lot weaker than intramolecular forces, okay? They become rapidly weaker as the distance between the dipole increases. So if you are pulling apart the two different molecules, it's going to be harder for them to attract to each other if they're farther apart. So it gets weaker as you increase the distance away. Another type of intermolecular force is hydrogen bonding. A lot of times we'll see hydrogen bonding with electronegative atoms like nitrogen, oxygen, or fluorine. And these are very strong because of the great polarity of the bond, because nitrogen, oxygen, and fluorine are all very highly electronegative. So because these are unusually strong, we have a specific group of intermolecular force, or IMF, intermolecular force, that's called hydrogen bonding. So hydrogen bonding plays an important factor in the boiling points and shapes of compounds containing hydrogen. So sometimes you might have to identify what type of intermolecular force is in this molecule or this compound. If it has hydrogen and it also has nitrogen, oxygen, or fluorine, it's going to be hydrogen bonding in addition to dipole-dipole interaction. Okay, so this is just a picture of water. So this right here is just one molecule of water, just to give you a reference. Okay, but over here in the B side, the dotted lines are your hydrogen bonding. That's happening from the hydrogen of one molecule to the oxygen of the other molecule. And this still follows the same rules of dipole-dipole interaction, because we really haven't done this very much, but remember our slight charges, hydrogen is always slightly positive, and the electron, or the oxygen, will be slightly negative because it has the unshared pairs left over on it from its Lewis structure. So the interaction is still happening from the slightly positive side of a molecule to the slightly negative side of a molecule. Okay, so that's hydrogen bonding. We've talked about both of those in Chem 1. The next type is London dispersion force. So sometimes you will have nonpolar molecules, but they still have forces that are holding them together. So this is evident to us because all substances can exist as a liquid and a solid under certain conditions, and in order for them to be a liquid or a solid, they have to be held together by some sort of force. So the forces that exist among noble gas atoms and nonpolar molecules are called London dispersion forces. Sometimes here in the notes I just simplified it and put LDF, London dispersion force. We called it just dispersion in Chem 1 last year or 2 years ago. I'm thinking about changing that because it's kind of confusing with dipole. But the London dispersion forces are forces that are created by electrons that move around the nucleus, creating a momentary non-symmetrical electron distribution. So normally, if it's nonpolar, it's pretty symmetrical, right? But then somehow the electrons get moved to create an uneven distribution, and it makes a temporary dipole moment, so that can make that have a force. Okay? So dispersion forces increase with increasing contact area between molecules and with increasing polarizability of molecules. This polarizability, I can't say it. I could say it earlier, but I can't now. Of a molecule increases with an increasing number of electrons in the molecule. So the more electrons you have, the greater the chance for this to happen. So it's enhanced by the presence of pi bonding And when do we have pi bonding? In a double bond or in a triple bond. So there's more electrons present in that bond because there's twice as many or 3 times as many electrons. And that's what makes London dispersion force possible. Okay? So it's also important to note that London dispersion forces exist between polar molecules as well, but they're not as strong as the dipole-dipole interaction. So we normally just say the dipole-dipole interaction. So a lot of times we have lots of different types of intermolecular forces between molecules, but we normally, you don't always think about every single one, because lots can be on the same, lots of different types of forces can interact. So this picture is in your textbook on page 457. This is showing this instantaneous dipoles that's created with London dispersion force, okay? So atom A and atom B have no polarization. So for example, if we had 2 H2 molecules, they're not polar, so they're nonpolar molecules. Well, something happens so that all of a sudden one of the atoms or one of the molecules will get an uneven distribution. So the electrons will move to one side. And by moving to one side, they create that instantaneous dipole, which would then induce a dipole in the other as well. And so, you have to have one get it started to then pull for the other one as well. And this one is kind of one of the weaker forces because this is not natural. They want to be nonpolar, and so it's a weak force because even though it instantaneously happens, it wants to go back to being nonpolar, so it will revert back to its original form. So the dipole-induced dipole interaction is kind of similar to what I just showed you, but instead of having 2 nonpolars, maybe you have a permanent dipole polar molecule next to a nonpolar molecule. And so the polar molecule will then induce a dipole in that nonpolar to have that same kind of interaction happening. The larger the magnitude of the dipole in the polar molecule, the better able it is to induce a dipole in its neighboring molecule. So the stronger that electronegativity difference, the more likely it will be able to have this happen. Just like London dispersion forces, nonpolar molecules with greater number of electrons have an increased polarizability. Gosh. This means that more electrons increases the ease with a dipole in which a dipole is induced. So this picture I have here, this is iodine chloride and xenon. And so xenon is the noble gas, so that's the nonpolar. But then the iodine chloride is inducing that, it's hard to see, but there's some lines right here. It's inducing to have that interaction between the xenon and the iodine chloride. Another type is called ion dipole interaction. This can happen when you have polar molecules attracted to ions. So this happens a lot when we dissolve things in water. So we learned in chemistry 1 that when something's dissolved in water or aqueous, that means it's broken apart into its ions. And we tried to explain that when it's broken apart into its ions, the water molecules go around the ions, so the ions can't get back together. That attraction between the water to the ion would be this ion dipole interaction. Okay, that would be a term for it. So this tends to be stronger than regular dipole-dipole forces. So that's why when we take sodium chloride and dissolve it in water, this is stronger than keeping the ions together. And so that's why this tends to be stronger, or that's why things stay dissolved, kind of thing. So with all of this information, the relative strength and orientation dependence of dipole-dipole and ion-dipole forces can be understood qualitatively by considering the sign of the partial charges that are responsible for the molecular dipole moment. So where are the partial charges on the molecule? And how these partial charges interact with an ion or with the adjacent dipole. So those two are very important to help you to consider whether it will actually take place or not. And so this picture, A, is a picture of just a non-polar oxygen molecule, O2. Okay, but then in B, water is the polar substance, and it is inducing a dipole by, so do you see how when it's nonpolar, the oxygen is very symmetrical, but when it's in the induced dipole, then it doesn't stay symmetrical. The slightly negative side is bigger. Why is the slightly negative side bigger? More electrons, exactly. So more electrons makes it bigger. And then the slightly positive side is smaller. And then it's attracted to, it has this attraction with the slightly negative side for those two unshared pairs of electrons on the oxygen in the water molecule. So this is just another way to show that. So we just have to be careful that we're aligning positive and negatives for the slight charges. And like oxygen in water is very strong because it has two unshared pairs compared to just one unshared pair. So just one unshared pair won't pull as much as two unshared pairs. Okay, last but not least, last year when I took the AP class to Purdue for a field trip, I haven't heard from them yet, we were focused, this is what our lab was about when we went. And so we focused more on how intermolecular attraction or intermolecular forces work in large biomolecules in that lab. And it was before we had gotten to that point in the year, and people didn't really understand, and people didn't remember how to do a lot of stuff. So it was a good and bad situation. But in large biomolecules, non-covalent interactions may occur between different molecules, or even between different regions of the same molecule. So protein structure, a protein will fold upon itself. So like all the proteins I have from Science Olympiad, that's all the same thing. But the reason why it's being folded together is because of the interactions between the different parts of that protein. So the functionality and properties of the molecule are largely dictated by these non-covalent interactions. This is an alpha helix picture where the structure, the actual structure, which it could be from that protein or not, is wrapping around this pole, and that's why they have the pole in the center, so you can see that it wraps like a helix around. But then what's holding it in that helix shape is the hydrogen bonds between itself. So that's one way that large biomolecules will interact with each other to form its shape, and that makes it do different things. This is called a beta sheet. So alpha helix and beta sheets, it make a pleated sheet kind of thing where they go up and down. And again, so this has two next to it, like in line with each other, going up and down. And the reason why they're next to each other is because of the hydrogen bonding in between the two molecules. When we were at Purdue, they had this like virtual reality game that you had to go in, and you like were like messing around with like a molecule like this, and you were just trying to find the best intermolecular force spots. I don't really understand it all that much, but this is an example of why chemistry is more important than biology, because you can't have DNA or all these structures unless you have hydrogen bonding within the atoms. So you can go take that to your other teachers for that. So that's the end of 3.1.